Welcome to the Explainer. Today, we're going to tackle one of the biggest questions in all of data analysis. When we see a pattern, how do we know if it's for real or if it's just, random chance?
Picture this. The students in Classroom 105 get 5 extra hours of study time, and bam, their average test score is an 81. Meanwhile, Classroom 106, who didn't get that extra time, they averaged a 74. So it seems like a no-brainer, right? The method is working.
But, and this is the big but every single analyst has to deal with, how can we be sure? How do we know those higher scores aren't just a total coincidence? Maybe the kids in 105 were just having a good day. And that's the whole game, really, separating a true effect from what's just random noise. So to get to the bottom of this for real, we can't just go with our gut. We need to level up from just noticing something to actually testing it scientifically. And the way we do that is with this awesome tool called the hypothesis test. Now, this is the bedrock of something called inferential statistics. Fancy term, I know. But all it really means is it's the science of taking a small piece of data, like our 2 classrooms, and making a really educated guess about the bigger picture. So here's the strategy. You basically set up 2 competing theories, like they're going head-to-head. First up, you've got the null hypothesis. Think of this as the ultimate skeptic. It's the default position that says, nope, nothing to see here. The extra study hours made 0 difference. And fighting against it is the alternative hypothesis. And that's our hunch. It's the idea that, yeah, the extra hours did make a difference. All right, so we've got our 2 claims facing off. One says our teaching method is a winner, the other says it was just a fluke. So how do we decide which one to believe? How do we build ourselves a reliable fluke detector? The whole point here is to figure out if our evidence is strong enough to just toss out that skeptical no difference claim, the null hypothesis, and say, yeah, something real actually happened here. But how strong does that proof need to be? So how do we measure this evidence? Well, we use a super important number called a p-value. The p literally just stands for probability, and it does one simple thing. It tells you the chances of seeing your results, the higher test scores, if it was all just random luck. And in most scientific fields, there's a kind of magic number we look for, 0.05 or 5%. Now you might ask, why that number? Honestly, it's mostly a historical thing, a convention scientists agreed on. It's like a sweet spot, right? It's strict enough that we're not constantly raising false alarms, but not so strict that we miss genuine discoveries. The bottom line is, if the probability of your result being a random fluke is less than 5%, you're probably onto something real. So here's the key takeaway. When your p-value dips below that magic 0.05 threshold, that's when you can declare your result statistically significant. That's the green light. It's your permission slip to say, hey, the difference we saw is so unlikely to be a fluke that we can confidently reject that skeptical null hypothesis and accept our alternative idea. Okay, but here's where it gets interesting. Getting that p-value, it's not like there's just one button you push. You need the right tool for the right job. Think of it like a mechanic's toolkit. You wouldn't use a wrench to hammer a nail, right? So let's peek inside the analyst toolkit and check out 3 of the most common tools. So going back to our classrooms, remember, we're comparing the average scores of 2 different groups. For that exact situation, the perfect tool is something called a t-test. It's built specifically to tell you if the difference between 2 averages is legit or just noise. But okay, what happens when your data isn't in nice, neat averages? What if you're working with categories? Like say you ask students how prepared they felt, very prepared, somewhat prepared, or not prepared, and you want to know if that feeling has any connection to whether they passed or failed. For a question like that, you pull out a different tool from the box. This one's called a chi-square test. It sounds complicated, but the idea is simple. It just compares the pattern you actually saw in your data to the pattern you'd expect to see if there was absolutely no relationship. And look at this result. The p-value is 0.031. Since that's less than our magic number of 0.05, we can say, yep, there's a significant link between feeling prepared and actually passing. All right, tool number 3. What if you want to get into a little bit of fortune telling? What if you want to see if one number can actually help you predict another one? For example, can we use the number of days a student shows up to class to predict what their final test score will be? For that, you're going to want to use one of the most powerful tools out there, regression analysis. Okay, so you've run your test, you got a low p-value, you're celebrating, right? But hold on,
because getting that significant result is honestly just the starting line. The real skill, the art of being a great analyst, is knowing how to interpret that result without jumping to the wrong conclusion. And trust me, it's really easy to do.
And you have to be super careful to avoid two classic blunders. First, there's a type 1 error. We call this a false positive. Think of it like a smoke detector that goes off when you're just making toast. It's a false alarm. You're claiming an effect when there really isn't one. The opposite problem is a type 2 error, a false negative. This is way more dangerous. This is when there's a real fire burning in the house, but your smoke detector stays silent. You completely missed an effect that was actually there.
And that brings us to, no exaggeration, probably the most important phrase in all of data science. You've definitely heard it before. Correlation does not equal causation.
Let's make this real. Go back to our attendance example. So we run our regression analysis, and it spits out this number called an R-square value. Its job is to tell us how much of the story one variable can explain about the other. In our case, that value is 0.235.
So what does that number, 0.235, even mean? Well, it's the perfect example of our point. It means that attendance only explains about 23% of the variation in test scores. The other 77%, that's everything else. Study habits, how much sleep a student got, what's going on at home, you name it. So yeah, attendance matters, but it's just one ingredient in a much larger recipe for success.
So let's zoom out. How does all this, the hypothesis tests, the p-values, the correlation, how does it all come together? Well, this isn't just about passing a stats class. This whole process is a powerful, practical blueprint for making smarter, more evidence-based decisions in the real world. It's a clear roadmap to a conclusion you can actually trust. First, you start with a sharp, clear question. That's your hypothesis. Second, you measure your evidence. That's your p-value. Third, you pick the right tool for the job. And finally, and this is maybe the most important step, you interpret your findings carefully, always chanting that mantra, correlation is not causation. Look, once you understand these core ideas, you're not just staring at a spreadsheet anymore. You're learning how to be a detective. You're learning how to separate the real signal from all the random noise, to find the truth that's hiding in the data. So the only real question left is, now that you know how to look, what stories are you going to find?